Hey folks, so today what we're doing is an activity where we'll be finding the coefficient of friction between the surface of this wood block and the countertop itself. Now that means we're finding mu, that coefficient of friction. And if you think about it, nothing I do aside from like gouging into the surface or like kind of changing the texture of this really should change the level of roughness between it. But we need a couple things to figure that out today. The first thing we need is this. It's called a spring scale, and it's actually, well, it's a spring. You can see right there behind that there is a little spring, and the farther I pull down, the more you see the spring stretches. And it's really important that we make sure that the little shiny silver marker there is right at the 0. And so we can kind of pull up and down on the tab here to kind of zero that out. And the neat thing is I could hang a 100 gram mass. Here's a 100. And if I do that, we can see that on the right side or the left side here, it shows grams. And we can see where my middle finger is at. It says 100. And we can see that the force pulling on this 100 grams is 1 Newton. So the force of gravity on 100 grams is 1 Newton. So what we'll do with this is the first thing we'll do is we got to hang our block. So I hang our block up, and let's take a look actually right here together with this. Hanging the block, we can see that we're right at about 2 newtons. So this is just around at 200 grams for my block. That does include the mass of the string though, absolutely, but that's okay. So what that tells us then is that when this block is sitting here, that gravity's pulling down on it with 2 newtons of force. But that also tells us that the table, the countertop, is pushing back up with 2 newtons of force to match it. Otherwise, the block would be accelerating up, or it would be accelerating down kind of through the earth. So aside from the spring scale and some masses, we're going to use a motion sensor. And these are pretty cool. They can open, and you can kind of set the setting to different things. But the way that they work is they actually work kind of like BAT's echolocation works. It sends out little ultrasonic sound waves, and you'll hear clicks if we kind of listen close here today. And those clicks bounce off an object and come back, and it tells us the displacement, how far away the object is from the little sensor here, and it tells us how fast the thing is going. And so the goal today is really what I want to do is I want to hook this up just like this, and I want to line it up so my motion sensor is right behind my block. And I want to pull my block in a straight line with a constant speed. Now, if the speed is constant, that means for us that there is 0 acceleration then, right? Well, if there's no acceleration, that means the force going forward and the force going backward are matched. They're equal but opposite. Because if one was bigger, it would start accelerating this way. If the other one was bigger, the friction force, which is resisting the motion, was bigger, then it would actually start slowing down because there'd be an acceleration this way. So the goal really is to make sure that I am pulling at a constant speed with this. And so that's what our motion sensor is for. It's there to kind of check me and make sure that I'm pulling really nice and even. Because if I pull nice and even, the pulling force this way and the friction force that way are equal to each other. And so if I pull nice and even and I read the strength of how hard I'm pulling, I instantly know that's the same as the force of friction backwards. So in kind of conclusion or summary, the force of gravity is the same size as the normal force. So we really know the normal force just by hanging this guy. And then by pulling it and looking at the value, we know what the friction force is because the pull this way is equal to friction that way as long as it's not speeding up or slowing down. So we'll do it once with nothing on here, then we'll do it again as we add more and more weight. And that's really all we're going to do. So first thing in our data table, we'll need to put down that the weight of our block, or the force of gravity on the block, is 200 grams. Okay, so this is just a quick check. All I've done is I put my motion sensor here, and I'm going to turn one of our little blue cars on because these guys should go at a constant speed. And so this will be a quick, great check to make sure that our motion sensor is working, and it kind of gives us the data that we want to get. both of these graphs actually indicate to us that, hey, that cart goes at pretty much an exact constant speed. We can see in the position and time graph because the slope is constant, and that slope represents the velocity. The velocity is constant, it's not changing. The velocity is constant, that means that car is not speeding up, it's not slowing down. We can see the same thing in the second graph here. There's a little wobble kind of right around here, but more or less, really, we just have a straight horizontal line. It's because that car didn't speed up, it didn't slow down. So that's just what we're looking for. And this is the same thing that we should see then when I pull that block across the countertop. Here's our first trial. We do have a 100-gram mass on the block. And we'll get going. Right, 1, 2, 3. The force looks nice and constant. Hopefully that's what you're identifying right now. So as we can see here, there's a little bump in the beginning as I pull, but really the velocity does stay pretty constant and the slope of the position graph does stay constant. So we can see that really that was at a constant speed. Here we go, pulling with the 200-gram mass now on top. A little bit of a surge in the beginning, but then it does seem to stay pretty constant. So you need to figure out what is that pull value. Here we can see, again, for our second pull with the 200-gram mass on top, yeah, there's a little bit of kind of like a bump in the beginning where it actually kind of has to go from stationary to kind of going a little quick, but then it levels back out. And from here on out, we see that it is pretty consistent. So again, that means my speed is constant. So that means that however hard I was pulling forward was matched by the force of friction backwards. There was no acceleration because we have this constant velocity. Trial 3 here is with 300 grams sitting on top of the block. And there we go. So this is the time that we really want to find that pulling force, which looks pretty darn constant. Again, with that 300-gram pull, I see here, I wasn't pulling it at all during this duration because the distance wasn't changing. We had this kind of spike as it jumped into motion, but then the speed or the velocity here stayed constant, just like we can see here, the slope remained constant. And if we really want to, there's some fancy stuff you could do here. You could go ahead and say, oh, put a linear fit on this, and it'll actually give you the slope of it, which would tell you the velocity. Last one here is with a 500-gram mass sitting on top of the block. Little spike, and then we stay nice and constant. That's it. So now that we know the pulling force for all of the trials of this experiment, and we'll see that just like with this one, again, we did have a constant slope here. We did have a constant velocity. With all these values, I need you to figure out what is that coefficient of friction, that measure of roughness between our wood block here and the counter.